Okay, so when we're hashing, what we're actually doing is we're carrying out a calculation. The idea of this is you transform a string of characters into something else. This is used within passwords. There's sort of things like the SHA-256, there's bcrypt. They're just different methods of applying a calculation to whatever data you've got that then creates an unrecognizable password. It's very good for security. We're not talking about that here though. That's just another usage of it, but I just wanted to mention it in case you've heard the term hash before and therefore you get an idea of what's going on. What we're doing instead is we're using the form of calculation to create the position in memory. Okay, so there's a slight difference. One for security, other for memory. So in the case of memory, you can see here that we've got a long piece of data, so 145721. By applying a mod to that, we'll get the remainder. In other words, we get 1 left over. That 1 can therefore be used as the memory location. It's much cheaper cost to find it, if you like, to get to memory 1 location than it is to get to 145721. Therefore, in location 1, we put in 145721. You can see we can keep going. So the 222833 would give us a mod 10 of 3 and therefore goes into location 3. When we're adding here though, we can have a problem. If we wanted to add 134721, because that would also give us a hash of 1, what would actually happen is the computer would try and put it here, but there's already data there. This causes what we call a collision, and therefore it will increment by 1 and we'll put it in the next available space. In this case, in position 2. However, if we've got a lot of collisions going on, what's going to happen is that it's going to look in position 1, you can't go. It's going to look in position 2, you can't go there, can't go in position 3. So therefore we'll actually put it in collision 4 position. And what you can obviously see there is you can create real inefficiencies with this. So ultimately, the best use of a hash is to use a calculation that doesn't create collisions. That's the perfect use. However, there is a solution, isn't there, to managing that if needed. When you're searching for it then, what you're having to do is you're looking for the data you're searching for. You carry out the hash on it, which will take you to position 1. That doesn't create a match, and therefore you need to look in the next one. Not a match, look in the next one, not a match, and then the next one, it is a match. If this for some reason wasn't a match, what we need to do then is look into the next available space, and if it's empty, that means you know for definite it's not in there. Okay, but in this case, it was there, and therefore we've found the item we were searching for. When we're deleting though, what you've got a problem then is because we're using an empty space to stop the search, if we were to delete an item, so in other words, the item in position memory 2 has been taken away, if that was left empty, if we were then looking for the item just as we did before, we'd look in position 1, and then we'd look in position 2, but because it's empty, it would stop, and therefore we wouldn't ever find the data in position 4. That's a problem. Instead, what we can do, therefore, is use what's called a tombstone. The tombstone is showing that that's an empty space of data, but it can't be considered as a pure empty space because that would stop the algorithm, and therefore it says that there was data once here, there was a collision once before, and therefore the computer knows to keep looking, of which it will then find the data and it's correct. Okay, another method for dealing with deletion and potential collisions is to actually use what's called separate chaining. The idea of this is you have your original hash table, but then in each index of the hash table, you then store a separate linked list. A linked list, as we already know, is easy to add to and delete from, and therefore manages that process of addition and deletion much better. However, what you are doing here essentially is creating ever greater memory usage. So in many ways, you've got to question, well, why are we doing this? So the idea of a hash originally was that we created the shortest path to any particular piece of data, but we accepted by doing so, we may get the occasional collision, which would then slow that process down. We've got a situation where we've got a lot of that happening, and we're then having to resort to having linked lists to store all of those collisions, we should then really question, is this the best method to use? Because again, we want to consider efficiency in data choices and data structure choices, and whether they're appropriate for it. We can do things like a folding method. Again, to carry out calculations, you can see here we take any number and we basically break it down into twos. So 03, 35, 23, 30, 34, and then a remainder of 5. Add that together and that becomes the memory location you're going to. Again, as I said before, we want to try and avoid collisions at all costs, really. We can also use ASCII values to do this. So we've got, a series of letters, we use their ASCII value and then just add those ASCII values together, can carry out a calculation with them, and therefore you can then have a word that then would go to a particular location in memory. Okay, well, I just wanted to say thank you for watching. I really hope you found it useful and really hope you've learned something. Please do like and subscribe, and I'll hopefully see you again. Thanks a lot. Bye.